Every piece of software you use, from a basic digital timetable to a massive social media feed, has to solve the exact same foundational problem. They all have to figure out how to physically organize and store data in system memory without causing the whole application to crash. Programmers face a strict choice right at the start. They can either dictate the exact memory footprint the program will need before it even runs, or they can build a system that scales its memory on the fly to meet demand. When you're first starting out, the ability to scale on demand feels like a universal upgrade. It's tempting to treat flexibility as the default setting, so you never have to worry about hitting a capacity wall. But choosing a data structure is a negotiation. You are deciding exactly how much predictability you are willing to trade away for that flexibility. Let's define the two sides. A static data structure is a system where the absolute maximum capacity is permanently locked in at the exact moment of creation. Because you tell the computer exactly how much space you need up front, the machine can set that block aside immediately. That hard-coded limit guarantees your program will execute with predictable, lightning-fast stability. The inherent risk of the static approach comes down to your estimates. Miscalculate the capacity by making it too large, and you waste precious system resources. Miscalculate by making it too small, and your program crashes when it runs out of room. On the other side, a dynamic data structure is a system designed to continuously grow, shrink, and request new memory blocks while the program is actively running. This fluidity prevents capacity crashes. As new data is introduced, the structure simply adapts, which theoretically allows for infinite scaling. To figure out which structure wins in a specific scenario, you have to measure them against three distinct metrics: memory efficiency, processing speed, and code complexity. This diagram shows the underlying mechanism of a static structure. The program reserves a single, contiguous, fixed block of memory before the data even arrives. In this case, a capacity of 5. Because this physical layout is set in stone, the computer's processor knows exactly where everything is. It can achieve extremely fast, direct access to any individual piece of data. But look at the two empty positions. Those slots act as dead weight. They are actively wasting system memory that other programs desperately need, simply because they were reserved in advance. And if you hit the limit, you have a severe problem. When a new piece of data tries to enter a full static structure, it gets rejected. The system cannot stretch the boundary. To accommodate that new data, it has to halt operations and build an entirely new, larger structure from scratch. That incurs a significant performance penalty. Static structures represent a highly optimized gamble. You achieve peak execution speed, but only if your initial capacity estimate was perfectly accurate. Dynamic allocation takes the opposite approach. Memory is only requested and consumed at the exact moment a new piece of data is added. This node-based approach matches memory consumption to actual user demand. By only allocating space as needed, you eliminate the issue of empty, wasted slots. But you pay for that flexibility with overhead. Every time this structure grows, the computer pays a hidden computational tax to manage these routing lines and run background resizing algorithms. That constant background management slows down raw data access speeds, compared to the direct pathways you get with static structures. There is also a secondary risk. Dynamic structures are entirely dependent on the host system. They can only grow if your machine actually has enough available memory to support that growth. Dynamic structures offer adaptability for user-driven applications, but they force the developer to pay a perpetual tax in processing speed and memory management complexity. Let's directly compare these architectures side by side to establish a definitive baseline for performance. For the allocation method, static locks contiguous blocks up front, while dynamic scatters nodes on the fly. When we factor in overhead and speed, the trade-off becomes explicit. Static offers zero resizing capability, but maximum speed. Dynamic offers infinite resizing, but costs you processing lag. The data proves that neither approach is inherently better. Their value is entirely inverse to one another, dictated by your specific project constraints. To map these computer science theories to real-world software architecture, we use a strict decision-making framework. The first question, is the maximum data size known in advance? If the bounds are absolute, like the 7 days of a week, or a strict 30-student class register, you follow the yes path. Static is the correct choice, guaranteeing hardware efficiency and zero overhead because the data is perfectly bounded. If you don't know the size, take the no pathway to a secondary condition. Must the program cope with constant, unpredictable changes? User-driven features, like a live print queue, streaming viewers, or a shopping cart, mandate a dynamic structure. Despite the heavier processing load, going dynamic ensures a seamless user experience that won't crash when traffic spikes. Professional architecture requires you to look past the label and account for the specific memory and speed costs of your expected volume. The ultimate rule for developers and exam takers is this: the architectural choice is dictated entirely by the predictability of the environment, not code sophistication. Locking in a strict memory footprint is a weapon for speed. Embracing overhead is your shield against unpredictability. Mastering data structures means mastering that return on investment. You must weigh the value of infinite storage against the raw power of guaranteed speed.